Usual introduction to the webinar platform in front of you, then hand it off to our featured speaker for today. If you'd like your slides to be bigger, you can expand the slide area or increase it to full screen by clicking on the arrows in the top right corner of the slide area box. If you have any questions during the webcast, just click the Q&A widget at the bottom of your screen. We'll answer as many questions as possible after the presentation. If you're having technical issues with the webinar, you can use the Q&A box to ask for help. We recommend logging off your VPN as well as closing any programs or browser sessions running in the background. Both of these actions will help your webinar run more smoothly. If the presentation freezes or you lose the audio, just refresh your browser window and this will solve the problem in most cases. Everyone will receive a link to the on-demand version of this webinar by email within 24 hours. GE will also issue training hour certificates to eligible attendees. Once you have attended at least 45 minutes of either the live or on-demand presentation, you'll be able to download a copy of your certificate from the webinar console. There will also be a certificate download link in your follow-up email tomorrow. That's it for the housekeeping. Now I'd like to turn the presentation over to our speaker today, Dan Ransom, Senior Technical Application Engineer at GE Grid Solutions. Over to you, Dan.
Good day to you. Welcome to this webinar, Today's Protection and Control Approach to Generator Protection. My name is Dan Ransom. Here's a bit about me. I'm from Washington State in the USA, with my education from Gonzaga University in Spokane, Washington, and Washington State University in Pullman. I'm a senior member of the IEEE, and I serve on many IEEE committees. I'm a licensed professional engineer in many U.S. states. In my job as a technical application engineer at GE, I help people with applying protection, communications, and control systems in industrial and utility power systems. Our discussion focuses on important generator topics for protecting the generator from major fault damage. The protections that I will discuss today are typical generator protections, differential protection for stator phase faults and stator interturn faults, stator ground faults, restricted ground fault protection, sub-harmonic injection for stator and rotor field ground faults, loss of field protection, and power swing blocking and out-of-step tripping. These protections can help you avoid costly rewinds and extensive downtime. For typical generator protection, let's begin with the IEEE IAS Buff Book. Although from 2001, it gives us a place to start. In drawing A on the left, phase protection for a single isolated generator on a low voltage system is from a voltage restrained or voltage controlled overcurrent relay, device 51V. If the voltage dips, as it would with a fault, the current pickup level gets more sensitive. You can place it either at the preferred location on the neutral side of the generator or in the alternate location at the terminal side of the generator. The voltage comes from the fused voltage transformer as shown. Add device 51G, a ground time overcurrent relay. Today, we could add a restricted ground fault or restricted earth fault element in small generator protection to add stator ground fault protection to the bottom 35% of the stator windings. Additional protection that should be considered for multiple machines on a medium voltage system with resistance or impedance grounding is in drawing B on the right. A ground time overcurrent relay protects for ground faults. It could also be RGF, restricted ground fault. A three-phase differential 87 is applied, reported in the Buff Book as instantaneous overcurrent relays, providing a self-balanced differential protection. This advice is from 20 years ago. Today, we would use a dedicated generator relay like Multilin G30, the 889, and the MICOM P34X series with a biased low-impedance stator differential 87S. Also shown, along with the voltage-controlled overcurrent 51V, are device 32, a reverse power relay for anti-motoring protection, and device 40, a reverse VAR relay for loss of field protection. For medium-sized generators, employ an 87 differential element for the generator primary phase protection as shown here. In addition, employ 3-phase 51V backup overcurrent relays, voltage controlled or voltage restrained. As before, use a 32 reverse power element for anti-motoring and a 40 impedance element, these are offset Mohs circles at minus 90 degrees, for loss of field protection. One is recommended, but with modern microprocessor relays, 2 elements are easy to apply and provide an alarm as well as tripping. Add a 46 negative sequence overcurrent for protection against unbalanced conditions, and you can include a 51G for ground time over protection on this impedance or resisted grounded generator. The buff book specifies these protections from 12.5 to 50 megawatts. These are the recommended protections: 87 differential, 87G ground differential, 51V backup overcurrent, 51G backup ground time overcurrent. You could use RGF here as well. 40 impedance relay, the offset Mohs circles at minus 90 degrees for loss of field protection. 46 negative sequence overcurrent relay for protection against unbalanced conditions from the system. 49 RTD temperature element to monitor stator winding temperature. 64F generator field ground. And shown here is a 60 voltage balance relay. Again, in modern relays, this function is from VT fuse failure. For large generators and corresponding generator step-up transformers, there are many elements. This drawing shows everything, including the utility auxiliary transformer UAT and its protection. Generator neutral overcurrent is monitored via an overvoltage element 59G across the neutral resistor and or a neutral overcurrent element 5051G sensing the neutral resistor current. Added elements include a distance element 21 that senses through the transformer, taking the transformer phase shift into account. There are volts per hertz over excitation 24 and frequency elements 81. In addition is out of step or loss of sync 78 and inadvertent energization 5027. The 87T is a unit transformer with protection by close-in opposing CTs. The transformers have low oil 71 and sudden pressure 63 through a Buchholz valve. The 87O is an overall differential. As the major part of the generator, we must pay special attention to protecting the stator windings against stator phase faults. Differential protection 87 is very sensitive to stator faults. It operates on the principle of current in equals current out. I like to say the goes inta equals the goes outa. Here we see the differentials for the generator 87G, the step-up transformer 87GSU, the utility auxiliary transformer 87UAT, the substation transformer 87T-SST, and an overall differential 87U. Differential protection is high speed, typically 0.75 to 2.5 cycles. There is no need to coordinate with other zones, and the main issue is security during CT saturation, when the signals from the CTs do not actually represent the power system current. Stator differential detects ground faults in low impedance grounded generators, but it cannot detect ground faults in high impedance grounded machines. There's too little ground fault current at 10 amps and less. We use other protections for this situation. There are a few ways to make a stator differential element. Some of these are with split windings and overcurrent elements, which I'll discuss later. The best method is the biased differential stator element 87S with 2 slopes and 2 breakpoints. The key variables used in the elements are the differential current ID on the vertical axis and the restraining or bias current IR on the horizontal axis. The relay takes the absolute value of the difference between the neutral side and the terminal side currents for ID. For restraint or bias, IR, the relay uses the maximum of the neutral side and the terminal side generator current magnitudes. This makes the percent differential element very stable. There's a minimum pickup of usually between 10% and 30% of nominal current. Slope S1 is for normal CT inaccuracies of 5 to 10%, and slope 2 is for large CT inaccuracies at large currents. The slope 2 settings are normally 50% to 90%. The two breakpoints B1 and B2 define the end of linear CT behavior, that's B1, and the beginning of CT saturation at B2. Percent differential protection operates on a per-phase basis. It is phase segregated. Here's a close-up of the CT connections for differential protection. Note that the CTs are wired in the differential convention with polarity dots away. In the IEC P terminology, the P1 connections are away, as shown. In the differential, nominal current flow for load has an angle difference of 0 degrees. The angles of the current on the neutral side CTs and the terminal side CTs are approximately the same. For percent differential, it is recommended that the terminal side CTs and neutral side CTs have the same ratios, but it is allowed for the ratios to differ. The maximum allowable ratio mismatch is 10 to 1. In the case of a mismatch, the relay scales the currents to the primary of the CT with the larger primary value, which is used as the CT reference for the percent differential element. Because CT saturation gives false current inputs into the percent differential element, we can get security via the CT saturation detector. The relay employs the CT saturation detector to counter the effects of severe CT saturation, especially with external faults. For an internal fault with no CT saturation, the operating point in this chart moves from the normal load restraint in the low region of slope 1. The movement is instantaneous into the operate region. With fast digital signal processing, modern relays can time the onset of CT saturation. We know that flux cannot be created instantly, and therefore CTs cannot saturate instantly. The electric field is a function of the magnetic field changing over time, as we see in this equation from engineering school. For an external fault, a saturated CT operating point goes right, increases current, before it goes up, shows differential current. The relay implements the saturation detector based upon the timings to declare an external fault and not trip. The relay is secure for external faults. The relay provides phase differential security via the directional element. For a disturbance, a fault with CT saturation, the relay checks the phasor angles of the neutral side currents, I and S, and the terminal side currents, ITS. An external fault on the left has a small angle difference less than 90 degrees. The direction detector declares an external fault when these currents are less than 90 degrees apart and the differential current is greater than 0.1 per unit. An internal fault on the right has angles around 180 degrees because of the wiring of the CT polarities. The direction detector declares an internal fault, DIR equals 1, for an angle difference greater than 90 degrees. The direction and saturation detectors combine for differential element security. Typically, external faults near rotating machines result in very large time constants in the fault currents. Similarly, upon energizing a step-up transformer, the inrush current is limited only by the machine impedance. In addition, sympathetic inrush can provide very significant and long-lasting currents. The relay uses saturation detection to provide additional security against improper operation during these events. In the logic diagram, the percent differential element is supervised by the saturation and by the direction detectors. When there is no saturation, the relay bypasses the directional test and allows percent differential operation. When saturation is detected, the element makes an additional check on the angle between the terminal side CT and the differential CT currents. If this angle indicates an internal fault, then tripping is permitted. If there's a significant saturation and the direction element says external, the OR gate has 0 and 0 as its inputs. The AND gate does not allow the relay to trip on percent differential. Transformer magnetizing inrush and sympathetic inrush can lead to large currents and saturation, which can false the differential elements. We can apply harmonic restraint and harmonic blocking. Typical ratios of second harmonic to the fundamental are 10 to 60%. Flux induced in the core is proportional to the magnetizing current. It is in quadrature with the applied voltage during steady state. The steady state flux cannot appear instantly because energy cannot be transferred instantaneously. This means that there is a current spike that lasts for a short duration before subsiding. This leads to predominantly second harmonic ringing, which causes differential element operation as an internal fault. There are two methods to combat this. One method is to set the digital relay to filter harmonics from the restraint current during inrush. Another method detects the second and fifth harmonics to block the differential element while these harmonics occur. For security, incorporate second and fifth harmonic blocking. Let's take a look at a big problem in generators, stator interturn faults. Interturn faults are short circuits of adjacent turns on the same phase in the stator windings. Interturn faults are difficult to detect. There is no difference between the neutral and terminal currents monitored by the 87 differential. Unbalanced 46 can detect this. In addition, for split phase generator windings, we can use the split phase element 50 SP. Here are some waveforms showing a fault. Phase A and phase B show increased current. The negative sequence current is substantial and picks up the negative sequence overcurrent element or unbalanced element, indicating a turn-to-turn fault. Another method is to detect winding interturn faults in split-phase generator windings by measuring the unbalance of currents in the two windings. A fault produces circulating current. In the split-phase wound generator, another method is to use two CTs to measure circulating current from an interturn fault. In addition, it can detect interwinding and interphase faults. Here are the details on using the split phase element for interturn faults. The steady state unbalance, or I bias, is a selectable slope times the load current I load plus the offset, which is the split phase current at no load. Settings for the split phase protection are to select a slope, which is biased by the load current, and to select the operating mode, which are over and over-under. In over mode, the element picks up if I split minus I bias is greater than the pickup, and the currents I load is above the minimum load. In over-under mode, the element picks up if the absolute value of I split minus I bias is greater than the pickup, and the load current exceeds the minimum load. Stator ground faults very near the neutral side terminals, the star point, are difficult to detect. Let's take a look at some methods for protection. The methods for detecting generator ground faults depends on the type of system grounding. A solidly grounded generator provides downstream elements with sufficient operating current. However, ground fault current can be greater than the three-phase fault current. In a resistance or low impedance grounded generator, the ground fault current is 200 to 400 amps. The generator can be damaged on an internal ground fault. A high impedance grounded generator exhibits little or no generator damage from ground fault because ground fault current is 10 amps and less. The system ground is from the generator step-up transformer. Hybrid grounding is a way to get the best of both worlds. It employs dynamic switching from low impedance grounding in normal conditions to high impedance when an internal generator fault is detected. When a ground fault occurs in the generator, the 87GD detects the fault. It commands vacuum switch VS to open, removing the low impedance ground, leaving the neutral grounding transformer and neutral grounding resistor. This high impedance path limits fault current to approximately 10 amps, and thus it stops generator damage. As the fault continues, the 59N27N takes care of tripping. Under normal operation, the low impedance ground provides a ground source for other zones. The 51G acts as backup protection for uncleared system ground faults. However, it is too slow for internal generator ground faults. In summary, hybrid grounding provides fault current for phase faults while protecting the generator for ground faults. It is popular in industrial systems. There are three main methods for low impedance and solidly grounded generators: 51G ground overcurrent, 67N neutral directional overcurrent, and 87GD ground differential. With parallel generators, the 67N shines. Unlike non-directional 51G elements, the faulted generator 67N trips for the generator ground fault. The unfaulted generator 67N does not trip and keeps that generator running. Here is the sequence of events. A generator ground fault occurs, shown on the right side. 67N and 51G detect the generator ground fault. 51G picks up in the unfaulted machine. This is a problem. 67N trips fast in the faulted machine, and the 51G resets on the unfaulted machine as well as the faulted machine, averting an unnecessary trip on the unfaulted machine. Another method for generator ground fault protection is ground differential 87GD. It's very selective. It clears generator ground faults per generator. You can use the 51G elements to detect catastrophic internal faults and for power system backup. An advantage of ground differential is that the ground switches on all the machines can remain closed. What's the coverage for ground faults in a low impedance grounded generator with 51G, 67N, and 87GD for protection? We can use these elements, however, phase fault protection does not provide full 100% stator ground fault protection. Left unprotected is the bottom 1 to 5% of the winding near the neutral. There are ways to protect this area. We'll develop these next. A 100% stator ground fault coverage can be obtained with third harmonic voltage. Our task is finding the third harmonic in generators. A third harmonic voltage is present in both the neutral side and in the terminal side of the generator. This third harmonic voltage varies with loading and the fault position on the winding. Under normal operation, in the top graph, you can measure negative third harmonic voltage near the neutral and positive third harmonic voltage near the terminals. If there is a fault at the neutral in the middle diagram, the voltage gradient declines from the terminal to the neutral side. If there is a fault at the terminal in the bottom diagram, the voltage gradient declines from the neutral to the terminal side. If third harmonic goes away, we can conclude that the ground fault is near the neutral. To sense ground faults on a high impedance grounded generator, enable a 27TN, a third harmonic neutral undervoltage element, to protect the bottom 15% of the generator windings. Because the primary third harmonic voltage is small, from 0.5 to 8 volts, the element must be sensitive. The 27TN element requires supervision for a loss of phase voltage. When the machine is not running, it cannot generate third harmonic voltage. In addition, the third harmonic varies as the load and power output varies. Therefore, it needs supervision from VAR, power factor, current, and power band. These are additional supervisions because third harmonic levels vary with the modes of generator operation, such as synchronous condenser, pumping, and VAR sync. Another method for stator ground fault protection is the third harmonic voltage difference ground fault protection, 59D64TN. It responds to third harmonic voltage measured at the generator neutral, which is Vn third, and at the generator output terminals, which is the third harmonic zero sequence voltage, 3V0 third. When used in conjunction with the 59, neutral overvoltage at the fundamental frequency, it provides 100% ground fault protection of the stator windings. The amount of third harmonic voltage that appears in the neutral side is both load and machine dependent, therefore we must use an adaptive protection method. The relay uses these formulas to create an adaptive operating quantity based on the amount of neutral voltage Vn third and the amount of terminal voltage 3V0 third. Combine these quantities for supervision. For a high impedance grounded machine, choose the neutral resistor such that the power dissipated in the resistor during a single line to ground fault is approximately equal to the reactive power produced by the zero sequence capacitance between the stator winding and the GSU low voltage winding, which is X0C. At the power system frequency, the neutral resistance is equal to X0C divided by 3, and at 3 times the power system frequency, Rn equals X0C. As mentioned, to complete the ground coverage picture, we need an element for mid-range, normal operation, as seen in the graph where third harmonic is small. If we use a fundamental frequency, neutral overvoltage 59N element, connected across the neutral grounding resistor in impedance grounded generators, we can get 90 to 95% stator coverage. For a unit connected generator with a delta Y step-up transformer, the ground source is a neutral grounding transformer, NGT. With 59N, we select a transformation ratio to provide 120 to 240 volts for a ground fault at the machine terminals. This example shows how to calculate the transformation ratio. It is important to note that close-in system ground faults are capacitively coupled across the GSU transformer. To summarize, we can get 100% ground fault coverage in high impedance grounded generators that are unit connected. I'll discuss another method, sub-harmonic injection, later. Ground fault protection is from third harmonic voltage difference, 59D64TN. It covers 0 to 20% and 80 to 100% of the stator winding. It responds to the ratio of neutral and terminal third harmonic voltages. There's 27TN, the third harmonic undervoltage, which covers 0 to 15% from the neutral end, and it responds to neutral third harmonic voltage. And 59N, the fundamental frequency overvoltage, which gives 95% coverage of the stator winding from the terminal end at the fundamental frequency of 50 Hz or 60 Hz. 100% stator ground protection maps on the stator windings like this. 59D64TN provides stator winding coverage at the bottom 20% and the top 20%, which is typical. It does not have a security problem with loading, as can 27TN. It requires 59N to protect the null spot at the mid-winding, and it needs Y-phase VTs, because we cannot obtain 3V0 from delta VTs. For small fault currents, primarily faults close to the neutral or star point of a Y-connected winding, the phase CT-based 87S is not sufficiently sensitive. The solution is to use the restricted ground fault RGF element, also known as the restricted earth fault element. The word restricted means focused on the area of the generator windings within the boundaries of the CTs. This protection method is fully capable of service. This protection is used mainly for small generators where the ground differential protection is not possible. An internal ground fault on an impedance-grounded or resistance-grounded Y winding produces a fault current that depends on the ground impedance and the fault position on the winding with respect to the neutral point. The resulting primary current is negligible. For for faults in the lower 35% of the winding because the fault voltage is not the system voltage, but rather the result of the transformation ratio between the primary windings and the percent of the shorted turns on the secondary. Therefore, the differential currents can be less than the slope threshold of the main differential element. The fault can go undetected. Restricted ground fault protection extends the differential coverage towards the neutral point. The figure here shows the basic applications and wiring rules. RGF is used on transformers and on generators. Often, RGF is applied to transformers having impedance-grounded Y windings. The RGF element is applied to the stator winding of a generator having the neutral point grounded with a CT installed in the grounding path. Alternatively, the ground current is obtained by external summation of the neutral side stator CTs, as shown in the lower right. An advantage of the restricted ground fault protection is greater sensitivity at the neutral end of the winding. The graph shows that the phase CTs provide very little output in the winding area close to the neutral point. Fast detection of close to neutral ground faults is an advantage of RGF. It is very secure and has good performance for external ground faults. And it has a configurable pickup, slope, and delay. Here are some considerations for the slope setting. It must be greater than the maximum expected differential, IGD, divided by IGR, to avoid tripping on through faults. The recommended setting is 40 to 70%. An example estimates the through fault CT saturation at 80%. The RGF differential for this through fault is 66.7%. Therefore, set the slope to 70%. Selecting better CTs means that you can lessen the slope setting. Restricted ground fault is slightly different in the UR 8 series and P34X relays. RGF calculations are those of a low impedance bias differential. The differential current is produced as an unbalanced current between the ground current of the neutral CT IG and the neutral current derived from the phase CTs. IN equals the vector summation of IA plus IB plus IC. This type of low impedance ground fault protection can have potential stability problems, especially for an external phase-to-phase fault. To counteract this problem, the UR restraining signal is the maximum of the sequence currents to cope with these stability problems for all types of faults, while providing fast and sensitive protection. In this block diagram, we see that in the UR, the ground differential current is a vector sum of the phase CT's neutral current, 3I0, and the measured winding neutral ground current, IG. The relay develops the slope by using the ground differential current, IGD, and I restraint, which again is the maximum of the zero sequence, IR0, negative sequence, IR2, and positive sequence, IR1 currents. There is a minimum pickup for IGD, and a timer to condition the element output. Here's the block diagram for the 8 series. The ground differential current is a vector sum calculated from the phase CT's neutral current, 3I0, and the measured winding neutral ground current, IG. The slope is developed by using IGD, the ground differential current, and I restraint, which in the 8 series is the maximum phase current. The P34X restricted earth fault calculations for the low impedance bias differential are shown here. Stability for external faults is from appropriate scaling for IREF bias. The differential current is produced as an unbalanced current between the neutral zero sequence current derived from phase CT's IA plus IB plus IC and the neutral CT IN input times a scaling factor. The neutral current scaling factor compensates for differences between neutral and phase CT ratios. Make certain that the CT ratios are programmed correctly. The IREF K1 bias level is applied to through currents up to IS2, which normally is set to the rated generator current. Additionally, IREF K1 is set to 0 to give optimum sensitivity for internal faults. However, if any differential spill current is present under normal conditions from CT mismatch, the IREF K1 can be increased accordingly to compensate. A setting of 20% is recommended. Typical settings for IS1 are 10 to 60% of the winding rated current when solidly earthed, and when resistance grounded, 10 to 25% of the minimum earth fault current for a fault at the generator terminals. The G60 and the higher-end P34X generator relays can use sub-harmonic injection to provide 100% stator ground fault protection. It works like this. Place a 20 Hz voltage source across the neutral grounding resistor via a coupling filter. Why a 20 Hz signal? Because it minimizes the effects of circuit capacitances shown here. Recall that capacitive reactance is 1 over 2 pi Fc, which is an inverse relationship with frequency. As the frequency goes down, the capacitive reactance goes up, and the system capacitances look more like large reactance open circuits. Normal current flows through the generator capacitances shown in the drawing. A fault causes current through the ground fault resistor Rg, creating voltage and current at the relay end of the grounding transformer. This method requires the sensitive ground input for the G60 and P34X relays. The relays calculate the ground fault resistance Rg by measuring the 20 Hz voltage and current phasors at the secondary of the grounding transformer. Normally, the measured resistance is very large. However, when the relay measures 10 to 5 kilo ohms primary, it alarms, and for tripping, the measured resistance drops to the range of 5 to 1 kilo ohms primary. An overcurrent element responding to the sub-harmonic provides backup protection. An additional module and filter are the equipment needed for 20 Hz injection. These are the GPM-S, which is the stator module, the GPM-S-B, the bandpass or coupling filter, and a CT204-SD-43737. You can also order a current transformer to couple the 20 Hz signal. When we look at stator ground fault coverage for a high impedance grounded generator, 100% stator ground protection based on sub-harmonic injection provides the coverage of the traditional three means of stator ground fault protection. The sub-harmonic injection 64S is available in the G60 and P345. The traditional three methods of stator ground fault protection are the 100% stator ground protection, 59D64TN, that uses the third harmonic voltage at the generator neutral and the third harmonic zero sequence voltage at the machine terminals, the third harmonic neutral under voltage 27TN protection at the machine neutral point, and the neutral over voltage elements 59N1 and 59N2. We can measure resistance in the field circuit with sub-harmonic injection to detect field ground faults. Field ground fault detection limits damage and reduces downtime. There are two methods: single-point injection, which gives application flexibility and diagnostic information. It identifies quickly the fault location in the field winding. Single-point injection cannot be used on generators with brushless excitation unless both sides of the field winding are directly connected to a brush. In addition to single-point injection, the injection module has double-point injection. Typically, double-point injection is used on applications where generators are equipped with static excitation. When the module is connected for double-point injection, the fault location feature is not available. If fault location is required, then you should use single-point injection. Use the GPM-F for square wave injection. The field ground injection frequency can be 0.1 to 3 Hz in steps of 0.1 Hz. If the rated field voltage of the generator is less than or equal to 600 volts, then a single device solution is provided in the GPM-F. If the rated field voltage of the generator is between 600 to 800 volts DC, then an external resistor box is provided to facilitate safer installation and operation. For agile relays, use the P391 for square wave injection. The P391 is a low-frequency square wave injection, coupling, and measurement unit connected to the rotor field circuit. It passes the rotor field resistance measurement to the P342, 3, 4, 5, and 6 relays via a DCMA loop. The injection frequency is selectable at 0.25 Hz, 0.5 Hz, and 1 Hz via a jumper. A block diagram of the field ground detection scheme using the G60, P34X, and the GPM-F is shown here. The field winding of a synchronous generator is represented electrically by the impedance ZF equals ZF1 plus ZF2. Under normal conditions, the field circuit is ungrounded. The capacitance CF is the stray capacitance of the field distributed along the field winding. This capacitance represents the only path for current to flow to ground under normal conditions. The resistance Rg represents a breakdown of the field winding insulation, providing a resistive path to ground through the field grounding brush. The insulation failure can occur anywhere, so the impedances ZF1 and ZF2 are unknown. The fault impedance Rg is also unknown. The purpose of the field ground detector is to measure this resistance. Measurement of Rg is accomplished by injecting a voltage V-inject and measuring the resultant current Ig. The measurement algorithm must be capable of discriminating between capacitive current from CF, which can be significant, and a resistive current due to the fault. The exciter voltage V field is a DC value with a small ripple, such that the impedance of the field is essentially resistive. The current I field is a DC current with a range of tens, hundreds, or thousands of amps. A brush liftoff condition prevents the field ground detector from operating. The relay senses a liftoff condition by calculating the RMS value of the ground current. Normally, it has a non-zero value from the capacitance in the field winding. A drop in this signal indicates an open circuit in the injection path. The field ground undercurrent feature detects this condition. A method of monitoring field current, device 76, is shown here. The relay can monitor the field current via a Hall effect transducer that produces a 4 to 20 milliamp output. Assign this signal to the field ground function to detect field overcurrent and undercurrent conditions. The maximum and minimum settings configured for scaling of this DCMA or Clio input are used to get the per unit values of field current. When a generator loses field excitation, it ceases to operate to provide power. Let's look at loss of field protection. A synchronous generator has an excitation system that supplies DC to energize the rotor field winding. This excitation to the machine rotor can be completely or partially lost because of various abnormal conditions, such as field circuit open or short, loss of supply to the excitation system, unintentional trip of a field breaker, and so on. Upon the loss of excitation, the synchronous machine acts as an induction machine, which can cause the machine to draw reactive power, VARs, from the system and overspeed, above synchronous speed. It is bad for the machine because the rotor surface heats from the slip-induced currents, and it is bad for the power system because stability is compromised and can suppress local voltage. The damage duration is based on the severity of the field loss. For a complete loss, we have only seconds, and the protection must be fast. For a partial loss, a small applied field, we have longer, from 10 seconds to minutes. Loss of excitation protection is applied to protect synchronous machines from these effects. Here are the synchronous machine capability curve and the operating limits. It is a composite of 3 different curves: the stator winding limit, the rotor heating limit, and the stator end iron limit. The capability curve establishes the steady-state generator operating limits. The stator winding limit is controlled by the stator current limiter, SCL. The curve also shows how the automatic voltage regulator, AVR, limits the steady-state operation to within the generator capabilities via the overexcitation limiter, OEL, and the underexcitation limiter, UEL. Loss of field protection works in the underexcited region. Loss of excitation protection uses positive sequence impedance measurements and two inverted offset Moe circles as shown here. The apparent impedance is affected by the initial generator loading. Here we see heavy loading and light loading, the system impedance, and the generator terminal voltage. Each circle characteristic can be applied independently. A Moe circle element measures whether positive sequence impedance falls within the circle. If so, the element operates with the corresponding delay setting. Further, a 20 millisecond reset delay enhances protection dependability, especially when the measured impedance jitters around a circle boundary. All impedance settings refer to the relay side impedance quantity, which is the CT-VT secondary side when looking into the machine. Although the setting values are in positive ohms, this protection function is looking into the generator, and hence the circle characteristics are shown reversed. The generator should stay synchronized with the power system. However, sometimes the generation and load balance goes out of kilter. This section explores power swings and pole slipping. Power transfer from the generator to the power system is described by the power and impedance formulas here. Power is maximum when the generator voltage EG and the system voltage ES is 90 degrees. The sine of 90 degrees is 1. Delta is the angle of separation between the two sources EG and ES. If the angle goes over 90 degrees, the situation can become unstable. This phenomenon is called out of step, OOS. There is reserve, margin, when operating at less than 90 degrees, shown at delta 0. An extreme power swing is when the generator does not track with the connected system. The dangers of this situation are that the machine goes out of step with the system, it accelerates and starts to slip poles. The results are damaging current pulsations, vibration, and heating. A transient stability study or graphical method establishes safe operation. We can define power swing blocking and out-of-step tripping like this. For power swing blocking, we prevent from tripping during power swings and slight out-of-step conditions. And we prevent the system from separating in an indiscriminate manner. Out-of-step tripping detects unrecoverable out-of-step conditions during the first pole slip. We initiate tripping of the circuit breakers to separate the system. Balance load with available generation on the isolated part of the system. The challenge is in detecting a power swing. Based upon impedance zones shown here, the relay must establish a blocking signal for stable power swings, establish a tripping signal for unstable power swings, measure positive sequence voltage and current, and block when the generator is offline or VTFF, VT fuse failure, is detected. From a power study, determine the number of characteristics between zone 1 and load. The two-step mode uses only the outer and the inner characteristics, so this leaves more space in heavily loaded systems to place two power swing characteristics between the distance characteristics and the maximum load, but allows only one or two determinations of the impedance trajectory. There are two modes of power swing operation. Two-step operation, where the impedance locus spends a finite time between the outer and the inner characteristics, and then the locus enters the inner characteristic and stays there for a time. In three-step operation, the impedance locus spends a finite time between the outer and the middle characteristics, and next a finite time between the middle and inner characteristics. Then the locus enters the inner characteristic and stays there for a time. Power swing tripping can be early or delayed. Early trip is trip on the way in. Selecting the early trip mode results in an instantaneous trip after the last step in the out-of-step tripping sequence is completed. The early trip mode stresses the circuit breakers because the currents at that moment are large. The delayed mode is trip on the way out. Selecting the delayed trip mode results in a trip at the moment when the impedance locus leaves the outer characteristic. Delayed trip mode relaxes the operating conditions for the breakers because the currents at that moment are small. The relay uses a detection construct to monitor a power swing. The total impedance, Z forward, is the sum of the step-up transformer reactance, ZTR, and the system impedance under maximum generation, Zn. Angle theta is the system impedance angle, the reach characteristic angle, or maximum torque angle. Add the generator transient reactance, X prime D. We can place a quadrilateral characteristic across this impedance, plus detection blinders. Note that the quad characteristic is greater than the reactance line, ZC, which is 90% of the transformer impedance. The angle delta is the power angle of separation between the two sources. If delta is greater than 120 degrees, the system is unrecoverable. Here is what happens for various power swing events. A power swing at high voltage is number 1, where we have out-of-step tripping on the way out. Number 2 is a stable power swing with out-of-step blocking. Here's number 3, another stable power swing. Pole slipping in the generating mode is an unstable swing where the locus moves from right to left and tripping occurs on the way out. And pole slipping in the motoring mode is an unstable swing where the locus moves from left to right and tripping occurs on the way out. We've come to the end of our session today. Here are some things to remember. There are many elements for generator protection. Choose wisely. 87S differential is fast and effective protection against stator phase faults. We can detect stator interturn faults with sensitive unbalance and split-phase differential elements. There are 2 ways to achieve 100% stator ground fault protection: third harmonic voltage and sub-harmonic injection. Restricted or focused ground fault protection is another effective method for detecting faults near the neutral. Sub-harmonic injection detects field ground faults. In addition, we can monitor for overall field current and for brush liftoff. We can use loss of field protection 40 as backup for the under-excitation limiter and prevent generator damage for low and no field events. Generator relays can monitor power swings to prevent separation on stable swings and slight out-of-step conditions, power swing blocking, and disconnect the generator to prevent damage from large, unrecoverable power swings, out-of-step tripping.
Thank you, Dan. Folks, we've got time for a short Q&A today. If you'd like to submit a question, please click the Q&A widget at the bottom of your screen, type your question in the text field, and click Submit. Dan, I'll hand it back over to you to begin answering questions that have already come in.
Well, we've come to the question and answer session, the part of our Tech Talk, where we've had some great questions come in during the Tech Talk and before, so I'd just like to address some of those now. Here's an interesting question. What is black start in generators? Well, black start is a condition where we've got to start the generator without significant power needed to operate the generator. Normally, in a large generator system, you have things like blowers, scrubbers, compressors, pumps for fuel, lubrication, cooling, and similar functions. as well as the power needed for excitation and control. So utilities specify certain special generation sites with usually batteries that can provide the sufficient power to get a smaller black start generator running. Then once this generator is up and running, we can use this power to start the larger generator. However, there's a problem when you switch the black start generator onto the line. And this was another question that came in during the body of the Tech Talk and the slides. Why does the generator trip when the GSU is energized? Well, switching energizes transformers, which exhibit large current inrush. And these large currents can trip the black start generator relays if the settings are not properly handled. A black start generator protection includes differential, and that rides through the transformer inrush. You've got to make sure that the differential is set so that inrush doesn't rip it off. So we've got modern digital relays that can detect the inrush and block the generator differential protection while it's sensing inrush, thus keeping the generator online, letting the transformer settle down, become operational. Most good 87 differentials are dual slope, and they compensate for CT saturation, as you saw in the slides. Also, that patented differential method that includes the saturation detector and the directional detector keeps the 87S differential element secure and the generator online. Oh, another question that came in during the slides. But 87 refers to any differential. 87S designates Stator differential versus 87G, which is the restricted ground fault differential I talked about in the slides. Here's another good question that came in. Generator application at a data center. Being a critical infrastructure, faster start and availability to deliver power is vital. So what are the protection functions needed to be in place? Usually data center generators are small, 1 to 4 megawatts. A bank of parallel generators takes about 15 seconds to start and synchronize, especially when you've got them in parallel. And during this time, the data center is on an uninterruptible power source, a UPS. So we must protect the generator windings from too much current. You can use the minimal 51V that I talked about in the slides early, the voltage controlled time over current, but it's slow. So I'm always a big fan of differential protection. Goes into matches that goes out, and 87 is fast. That is the best protection for data windings and for the lower parts of the windings, 87S and 87G. The relays, modern relays, are fast, so it doesn't affect the ability to get the generators, the data center generators online, take over from the UPS. Other protection elements I would include would be reverse power, just in case something doesn't switch, and loss of field 40 elements. The field is a problem. Usually not. As I referenced earlier just a little bit ago, switching the generators onto the data center power system could cause downstream transformer inrush and CT saturation. So again, good inrush blocking and dual differential slopes and saturation detection, directional detection at 87. Another question that came in, why is there distance protection in a generator protection relay? Well, often people want to detect faults out in the power system. Beyond the point of interconnection or POI, a generator relay with a distance element can sense faults in the power system and take the generator offline. Of course, when you set this up, you have to consider NERC PRC24 and PRC25, which define the frequency and voltage excursions, and 25, the generator loadability, during which the generator must provide power for other elements in the system to provide their protection function downstream. So the distance element in the generator protection relay can look through the generator step-up transformer. Then you can detect, well, usually phase faults, If you have a Y delta GSU, which most are, then not going to have a zero sequence or grounding path. So are difficult to see generator or system ground faults from the generator relay using a distance function, but it does work in some special applications. Why can't we run the generator at unity power factor? Well, usually we run it lagging around 0.8, not at unity, because that gives us more field excitation control current. There's little room for the voltage regulator to have control running at unity, so operating at 0.8 lagging leaves lots of room for the exciter to control terminal voltage. It looks about like all the time we have for our session today. I'll turn it back to you, Ta-Sin, to complete our session.
Thank you, Dan, and thank you everyone for attending. As mentioned before, you will receive a link to the on-demand version of this webinar by email within 24 hours. Please take a moment to fill out the survey at the end and let us know what you thought of today's presentation. This wraps up today's webinar. We look forward to seeing you again at our next Tech Talk on motor signature analysis. Have a wonderful rest of your day. Thank you.